Okay, 7. Below is the graph of the derivative. Oh, this picture is the derivative. This picture is the derivative. For what values of x is the function increasing? And for what values of x is the function concave down? Okay, so if you remember, we had that chart that related the function, the derivative, and the second derivative to one another. And it says if the derivative is a positive number or above the x-axis, the function is increasing. If the derivative is a negative number or below the x-axis, the function is decreasing. If the derivative is increasing, then the function is concave up. If the derivative is decreasing, then the function is concave down. So derivative positive, f increasing. Derivative, negative, f decreasing. Derivative increasing, f concave up. Derivative decreasing, f concave down. Okay, so this guy is positive on that side and negative on this side. So we need to know what that number is. I gotta make it bigger on this screen over here. So it crosses at 3, right? So before 3, the derivative is negative. After 3, the derivative is positive. So before 3, the function is decreasing. After 3, the function is increasing. So before 3, it's decreasing. Decreasing from 0 to 3, increasing from 3 to 8. 8. Just tip your head sideways. I can't make this work today. 8. Okay. Let's get this guy back. Okay, this is the derivative. When the derivative is increasing, the function is concave up. When the derivative is decreasing, the function is concave down. This guy is increasing. Oh, I can't write on him. And he's gone. This guy is increasing from 1 to 4 and from 5 to 6. He's decreasing from 0 to 1, from 4 to 5, and from 6 to 8. So this guy will be concave up from 1 to 4 and 5 to 6, and concave down from 0 to 1, 4 to 5, and 6 to 8. So concave up from 1 to 4 and 5 to 6. Is that what it was? Yep. Concave down from 0 to 1, 4 to 5, and 6 to 8. Okay, this one said, where is it increasing? So 3 to 8. I can't do an 8. Where is it concave down? 0 to 1, 4 to 5, 6 to 8. Where is there a local minimum? So this guy goes decreasing and then increasing. So what happens here at x equals 3? That's where the local minimum is. And then where is an inflection point? What are inflection points, you remember? Where the concavity changes. So at 1, at 4, at 5, and at 6. So 1, 4, 5, and 6. Concavity changes. Okay. That was number 7. Number 6. At exactly 2 of the labeled points in the figure below, which shows a function f. Okay, so this graph is of the function. So at exactly 2 of these points, the derivative is 0. The second derivative is not 0 at any of the points. Select the correct signs for each of F, F prime, and F double prime. Okay, so let's see. What's happening here at point A? It's a minimum, right? Is F positive or negative? Is the function positive or negative?
Negative.
Negative, because that Y value is below the x-axis. What about F prime?
What function are we looking at?
This blue picture. We're looking at point A.
Yeah, but what is that? Is that F?
The blue one is F, yeah. Yeah, it shows the function F. The blue one is F. So what would you say F prime is at this point A? This is a minimum, right? What's the
Zero.
derivative? Yeah, 0. Okay, and F double prime? F double prime tells you concavity, right? So at A, what do you know about the picture? It's concave up. So F double prime is what kind of number? Positive. Because it's concave up, it's a minimum, it's below the x-axis. Okay, how about at point B? Point B is over here. So it's above the x-axis, so this guy is positive. It's increasing, so F prime is positive, and it's concave down, it looks like. So this guy's going to be negative. Okay, how about point C?
Why is it concave down?
Because it's down like a frown. It's turned upside down. Right here at B.
Oh, you have a different view.
Oh, yeah, my graph might be different than yours. F prime, F double prime. Okay, so I'm at point C now, which is this guy up here. Okay, he is above the x-axis, so positive. He's a maximum, right? What's the derivative? What's the value of the derivative at a maximum?
0.
0. And is he concave up or concave down?
Concave down.
Concave down, so negative. Okay, point D. F prime, F double prime. D is that guy over there. He is above the x-axis, decreasing, concave down. Yes, at point D, we are above the x-axis, decreasing and concave down. So the function is positive. The first derivative is negative, and the second derivative is negative because he's above the x-axis, decreasing, concave down. Okay, last one, E. F prime, F double prime. Okay, let's put E over here. This one. Okay, he is below the x-axis, increasing, and what kind of concavity does this guy have?
Up.
Concave up. So below the x-axis, increasing, concave up. Below the x-axis means F is negative. Increasing means F prime is positive, and concave up means F double prime is positive. So negative, positive, positive. Okay, 3. The altitude of a triangle is increasing at a rate of 2.5 centimeters per minute, while the area of the triangle is increasing at a rate of 2.5 square centimeters per minute. At what rate is the base of the triangle changing when the altitude is 10 and the area is 81? Is this a related rates or an optimization question?
Related rates.
This is related rates because it says at what rate is it changing? What words do they give you in an optimization question?
Rate.
That's a related rates question. What words do they give you in an optimization question?
Most, best, least.
Yeah, maxes or mins, right? Highest, lowest, most, least. Yeah, fastest, slowest. So this is related rates. When we solve a related rates question, we draw a picture. What should I draw a picture of?
The triangle.
A triangle. Okay, here's a triangle. I have a base B and an altitude or a height H, right? 2, we label the known quantities. Okay, this says the altitude of the triangle is increasing at a rate of 2.5 centimeters per minute. What does that tell us about the triangle? dH dt is 2.5 centimeters per minute. The area of the triangle is increasing at a rate of 2.5 square centimeters per minute. What does that tell me? dA dt is also 2.5 centimeters squared per minute. At what rate is the base of the triangle changing? That's what I have to find, dB dt. When the altitude is 10 and the area is 81. At what rate is the base of the triangle changing when the altitude is 10, the height is 10, and the area is 81? Okay, so I need an equation that relates area, base, and height. Do you know an equation that relates area, base, and height? The area is equal to 1/2 base times height. Absolutely. Okay. And now what do I do? No. Take the derivative with respect to t. What do I need to use on the right-hand side here? The product rule, because b and h are both changing with respect to t. So I need the product rule on the right-hand side there. Okay, so dA dt is, I'm going to make this function f and this function g. So the derivative of f is 1/2 dB dt times h plus 1/2 b times dH dt. Okay, so I'm trying to plug in what I know, right? What am I trying to solve for again? I'm trying to solve for dB dt, this guy. So I need to know dA dt. Do I know that value? Yes. Do I know h?
Yes.
Yes. Do I know dH dt?
No.
I do, but it's up here. Yeah. Yes. Do I know b? No, I have to solve for b first. I'm going to solve for b first. I have this information. I'm going to use that to solve for b. Area is 1/2 b times h. 81 is 1/2 b times 10. B equals, let's see, 10 times 1/2 is 5, divide by 5, 81 over 5. Okay, now I'm going to plug in all the pieces that I know. The ADT was 2.5, 1/2, dB dt is the thing I'm solving for, times h, which was 10, plus 1/2 b, 81 over 5, dH dt, which was also 2.5. Okay. 2.5 equals 1/2 times 10 makes 5 dB dt plus, I'm going to find this number. So put this number in your calculator and see what you get. 1/2 times 81 over 5 times 2.5. So you're doing 1/2 times 81 over 5 times 2.5.
20.25.
20.25. Anybody else? Yep. Okay, I'm trying to get dB dt, so I have to subtract 20.25. So that's 18.25 negative. I don't know, someone subtract that. 2.5 minus 20.25. 17? 17.75. Okay, and then I'm gonna divide by 5.
3.55.
Negative 3.55. Negative, yeah? So what's happening to the base? It's decreasing by 3.55. What kind of units should I put there? Centimeters per minute. So the base is decreasing because it's a negative 3.55 centimeters per minute. Okay, 9. A rancher wants to fence in an area of 1 million square feet in a rectangular field, and then divide it in half with a fence down the middle parallel to one side. Okay. What is the shortest, there's one of our words, length of fence that the rancher can use? Note, the answer to this problem requires that you enter the correct units. Okay. A rancher wants to fence in an area of 1 million square feet in a rectangular field and then divide it in half with a fence down the middle parallel to one side. What is the shortest length of fence that the rancher can use? So shortest means maximum or minimum? Minimize. Minimum fence. Okay, so here's my picture. Yeah, I have a rectangle. I'm going to put a fence in the middle to make 2 pens. Okay, I'm going to label some sides here, right? I'm going to make the bottom and the top both be X because they go in the horizontal direction. And I'm going to make these 3 sides here be Y. Yeah? So I have an X here, I have an X on the top, and I have a Y here, a Y here, and a Y here. So how much fence does this guy have to use?
2x plus 3y.
2 X's plus 3 Y's. Yeah? How do you find the minimum of something? You take the derivative and set it equal to 0. The problem is that this guy has too many variables in him, right? So we need a helper so that we only have one variable in this guy. What haven't I used yet? Area. Helper is that the area is 1 million. $1 million. How do you find the area of this rectangle? X times Y is 1 million. I don't care whether we use X or Y. Y equals 1 million over X. So in here, instead of writing Y, I'm going to write 1 million over X. F is 2X plus 3 times 1 million over X. So F is 2X plus 3 million X to the negative 1. I'm going to write it like that because then my derivative is easier. Okay, to find the maximum, I take the derivative. I'm sorry, to find the minimum, I'm minimizing. I take the derivative, I set it equal to 0. So derivative of 2x is 2. Derivative of 3 million x to the negative 1 is negative 3 million x to the negative 2. I want to set this guy equal to 0. So 2 minus 3 million over x squared. Yeah? Okay, let's multiply every term by x squared. So 0 is 2x squared minus 3 million. Add 3 million to the other side, divide by 2. X squared is 1.5 million. X is square root of 1.5 million. Not my answer though, right? Because my answer said what? How much fence do you need, right? So I know that this side here is going to be square root of 1.5 million. What are my units on this side right here? Feet, yeah. So square root of 1.5 million feet. To find the total number of fence, I need to know this value. Yeah? To find the total amount of fence, I need to know this value, the fence value. So I'm going to take that value for x, and I'm going to plug him into that fence equation. So I'm going to say fence is 2x plus 3 million x to the negative 1. So the fence is 2 square root of 1.5 million plus 3 million times square root of 1.5 million to the -1. I'm going to get that number and I'm going to say that many feet. Blah. What's the square root of 1.5 million? Oh, okay. I guess we are going to get it right then. Shoot. Great. 4898 point like 98.
Yeah.
Yeah. Awesome. That's the right answer. Someone's good when we get it right. So I can't just give the X value, right? The X value is just one of the sides of the fencing. If it wants the total amount of fence, I have to take that X value, plug it back into my fence equation.
You plugged it into the equation without y. Is there a way you can figure out with?
You could, yeah. So if you wanted to, you could put your 1.5 square root 1.5 million into the area and solve for y. And then you would know that X is square root of 1.5 million. And y is whatever you find when you plug it in there. Yeah, either one's okay. Okay, 35. We're going in random order. It's fine. 35. If f is a differentiable function, find an expression for the derivative of each of the following functions. In submitting the answers, write f of x as f and f prime of x as g. So when we write the answers, I'm going to have to remember that. Okay, I want to take the derivative of x squared f of x. What do I need to use to take the derivative of this guy? The product rule. Okay, derivative of the first is 2x, leave the second alone, plus first times the derivative of the second. Remember that this guy goes in as f, and this guy goes in as, and this guy goes in as g. So this answer will look like 2xf plus x squared g. Keep going, all the parts? I don't know who asked this one. Yeah, all the parts? Yeah. Okay. B. Y equals f of x over x squared. Which rule do I need to use to take the derivative of this guy? The quotient rule. Y prime is bottom times the derivative of the top minus top times the derivative of the bottom over the bottom function squared. And then again, remember this guy is g and this guy is f. So this is going to look like x squared g minus 2f times 2x over x to the fourth. So he's going to look like x squared g minus f times 2x over x to the fourth. C should be exactly the same, yeah? Yeah, because it's just upside down. So you'll just, fix it when you type it in. Let's do D. 1 plus x f of x over square root of x. D. Y equals 1 plus x f of x over square root of x. Okay, I'm going to write this as 1 plus x f of x over x to the 1/2, because that makes my derivative life easier. Okay, so this needs a quotient rule. And what else does it need?
Chain.
A quotient rule and a product rule because of that x f of x. So this needs a quotient rule because you have the x squared and the x to the 1/2 in the denominator. and a product rule because of this x, f of x. Okay, so we say bottom, x to the 1/2, times the derivative of the top. To take the derivative of that top function, I have to use the product rule on this guy right here. So the derivative of that guy is going to be 1 f of x plus x f prime of x minus top 1 plus x f of x times the derivative of the bottom, 1/2 x to the negative 1/2 over the bottom function squared. And then we remember this is f and this is g. So when you type those in, make sure you put f for the pink ones and g for the yellow one. You could simplify this, but you don't have to. If you type it in just like that, it's going to work out. So are you ready? Yeah. Ooh, this one's really similar, except after we take the derivative, we're going to plug in numbers to get those values, okay? So little h is f of g of x. How do I take the derivative of f of g of x? Nope. How come this one's different than the other one?
Take the derivative of f of g of x is derivative of g prime of x.
Yeah, so this is like what rule is that called? Remember? This one's different than the product rule because in the product rule, you need two x's multiplied together, right? This one has the two functions stuck inside each other. What do we call it when we do the derivative of two functions stuck inside each other? Chain rule. This one I need the chain rule, yeah? If there's only one x and it's just multiple functions acting on that same x, you use the chain rule. If there's two x's and they're multiplied together, that's when you use the product rule. So this guy's going to look like h prime of x is derivative of the outside, leave the inside alone, times derivative of the inside. So f prime of g of 1 times g prime of 1. Okay, g of 1 is this guy. G prime of 1 is this guy. So then I have f prime of 2 times 6. Now I got to go back to the table one more time and look for f prime of 2. F prime of 2 is here, 5. So 5 times 6, 30. The other one is going to be the exact same thing, except my functions happen in the opposite order. So when I do the derivative, I'm going to get g prime, leave the inside alone, times f prime of x. And I'm still plugging in 1. So g prime of f of 1 times f prime of 1. So then I look at my table. F prime of 1 is that guy, 4. And f of 1 is this guy, 3. So g prime of 3 times 4. Okay, g prime of 3 is this guy, 9. So 9 times 4, 36. Okay, 13. Find the family of antiderivatives of this function. So I want to take the antiderivative of this guy. So you could do this with u substitution if you wanted. You could let u be e to the negative 5x, find the du, do it that way. And then let u be 3x, find the du, do it that way. But we memorized rules for these. Remember what they were? The antiderivative of sine of 3x is negative cosine of 3x divided by 3. The antiderivative of e to the negative 5x is e to the negative 5x divided by negative 5. So remember, whenever there's just a number here, you can just divide by that number at the end. It's kind of like the opposite of the chain rule. So the antiderivative of this guy is going to be 4.5 e to the negative 5x divided by 5. Antiderivative of sine is negative cosine divided by 3 plus c. So those are on our little chart there. E to the ax is 1 over a, e to the ax. And sine of ax or cosine of ax is negative cosine ax over a, and sine of ax over a, or 1 over a in the front, however you want to remember it.
Chain rule derivatives or antiderivatives, we cannot do product rule and quotient rule.
Correct. The chain rule is called u substitution. So with these rules, we're kind of doing the u substitution in our heads. Because these we use often enough that it's easier to just think of them like that. Okay, 19. Okay, 19, notice that in 19, these three integrals all go from 7 to 10, right? If this integral goes from 7 to 8 and this integral goes from 8 to 10, how do I get an integral that goes from 7 to 10? Add them up. Yeah. So to go from 7 to 10, I'm just going to add these two things together. Same thing here. To go from 7 to 10, whoops. I'm just going to add these two things together. Okay. So f from 7 to 10 is going to be 2. And g from 7 to 10 is going to be negative 8. So if I want f plus g, I'm going to do 2 plus negative 8. If I want f minus g, I'm going to do 2 minus negative 8. If I want 2f minus 4g, I'm going to do 2 times 2 minus 4 times negative 8. So the important part is that you have to look at these values over here first and see where do they want the integral to go from, and then find them with the integrals they give you. Okay, let me see what I got left. 37. Oh, man. Okay. I'm going to rewrite it as cosine e to the x squared sine x to the 1/2. So I'm going to start with this outside function 1/2. Then I'm going to move into the cosine. Then I'm going to move to the e. And then I'm going to move to this exponent up here. When I get to that exponent up there, the x squared sine x, what rule do I need to take its derivative? The product rule, because there are two pieces, right? The 1/2, the cosine, and the e are all stuck inside each other. That's a chain rule, yeah? When I get to this last purple part at the very end, I'm going to need to use the product rule. Okay, derivative of something to the 1/2 is 1/2 something to the negative 1/2. The inside function doesn't change at all. Whoops. Okay, times, now I'm covering up the 1/2 and I'm doing the cosine. Derivative of cosine is negative sine. Derivative of cosine is negative sine of something. The something doesn't change. E to the x squared sine x. Okay, times, I did the 1/2, so I cover it up. I did the cosine, so I cover it up. Derivative of e to something. Derivative of e to something is e to something. Times, I'm left with just that purple stuff, right? X squared sine x. How did I say I was going to take the derivative of x squared sine x? Product rule. So derivative of the first times the second plus first times the derivative of the second. So 2x sine x plus x squared cosine x. I think that infinity. No, because derivative of sine is positive cosine. It's tricky. Once we get to antiderivatives, everything falls apart. We can't remember the rules anymore. Could be. There was not this one. Yeah. It's like 7 and 15 or so. 7 on the handwritten part, and then like around 15 on the Edfinity. I can't remember exactly, but it's about that. Yeah. 1 hour for the handwritten from 11 until 12, and 90 minutes for the Edfinity from 12 to 1:30. I don't think I'm done yet though. I think we had one more maybe. I think that's what's left, yeah. Wait, what? We did 39, they tell me. Let's find it. There it is. Yeah. Other questions from the homework, from the Edfinity review?
It's like you think of any like super hard at related rates or optimization problems.
I mean, it's never the intent of a final exam to ask super hard things, right? Like that should never be the plan. Okay, let me stop the recording. End my meeting.